Hey guys, a lot of students often struggle with banked tracks, and in this video I just wanted to show you how I analyze banked track questions. So to understand banked tracks, you first need to understand why we have banked tracks in the first place. So let's look at an example. Here, what we can see is a velodrome. Now, a velodrome is a type of stadium that is used for cyclists in a race. And what you'll notice here is that the stadium or the track is usually always going to be banked at some angle theta. Okay. Now, why does this occur? Why would you want to bank a track? Well, it's because when you perform a force analysis on this banked track, which we're going to do over here. So what we're going to do is we're going to take a cross-sectional view, right? So here's my cross-section. So I want you to imagine this. The cyclists are sitting or riding along the banked track. And so when you think about the forces that are acting on the cyclists, you know there's going to be a force due to gravity acting downwards. We call this the gravitational force. And there's also going to be a normal force that is perpendicular to the surface. Okay? And so if you think about what's happening here, right? Why do we bank the track, or how does a banked track help the cyclist? Well, it's because, remember, that when a cyclist is traveling around this path, it's making a circular loop, right? It's making a circular path. And so by definition, it has to be undergoing uniform circular motion. Now, what do we know about uniform circular motion? The definition of uniform circular motion is that, by definition, if an object is traveling around a circular path, the net force must be equal to mv squared on r, right? The net force towards the center of the circle must be equal to mv squared on r. So here, because these cyclists are traveling around a circular path, it means that the net force acting on the cyclists must be in this direction equal to mv squared on r. That is to say that all the forces must add up to this amount, true? Now think about it. If you're on an inclined plane, what we are saying here is that the normal force is going to be perpendicular to the surface. Now, because the surface is banked, can you guys see here how there's always going to be some component of the normal force, which we're going to call fx or fnx, right? The x component of the normal force is always going to be pointing towards the center. That is to say that there's always going to be an additional force that's helping you push the object towards the center. So the reason why the reason why these tracks are banked is because it helps the cyclist provide the centripetal force. And so when the normal force provides some of that centripetal force, it makes it easier for the cyclist to turn, right? And you can see that because if you zoom in, are these cyclists turning their wheels? No. It's straight, right? Why? Because you don't need to turn to make the turn, if that makes sense, right? So that's the point of a banked track. Banked tracks help you turn the vehicle without physically having to turn the wheels. Okay? So it lets you go faster, right? That's the idea. So to summarize, banked tracks aid uniform circular motion by taking components of the normal force and projecting it towards the center of the circular path. What does that mean? It means that this x component of the normal force here is pointing in the direction of the centripetal force, hence it provides the centripetal force. Okay? So this applied force contributes towards the centripetal force, allowing vehicles to turn around a circular path without the need of friction or with reduced friction. We'll talk about that later on. And lastly, the speed of a vehicle, the speed that a vehicle can travel around a circular path without the need of friction is also known as the ideal speed. So what does this mean? It means that as the object travels around a circular path, there's a specific speed that you can go at without needing to turn. And that's what we call the ideal speed. In other words, if I'm traveling fast enough around a circular path, I don't need to turn my wheels in order to make it around the circle. I can just travel, I can just focus all my energy in going into a straight line. That's what we're trying to calculate. So what is this ideal speed, right? How fast are these cyclists moving such that they don't need to turn their wheels. Okay, that's what we want to calculate. Now, what does that mean? The ideal speed, right, remember, means that we don't need friction. So in other words, when you're looking at the forces, there is going to be no frictional forces required. So the speed that you can travel at without friction is known as the ideal speed. Let's go ahead and calculate that together. Now, in order for us to calculate or derive the expression for the ideal speed, there are 4 rules that you need to follow. And these 4 rules are true for any type of uniform circular motion question. So you can actually apply this to any scenario, and it's going to help you guys out a lot. So the rule is, step number 1, always start by drawing a free body diagram. Okay, now we've already done that here. As you can see, this is my free body diagram, yeah? Step 2 is to identify your F net X and your F net Y. So what this is going to do is you're telling yourself, okay, we know what the motion is. It's uniform circular motion. What does that mean in terms of forces? It means net force in the X direction needs to be what? And net force in the Y direction needs to be what? Okay, again, I'm just writing down the rules for now. I'll show you how to do it later on. Step 3 is to then resolve your net forces. What does that mean? Resolving net forces means plugging it in, right? You know what the net forces needs to be. We now need to plug in the expression. Again, I'll show you how to do this later on. And number 4 is simply solve, okay? And these 4 rules here, you can apply them to any circular motion question and get the answer. So we're going to use this rule to solve for the ideal velocity for bank track questions. Okay, so let's have a look. Step 1, already done. Let's move on to step 2. So step 2, what do we say it was? Step 2 is to identify the net forces in the X and the Y axis. So what's F net X? F net X is the net force in the X direction. You can see here how the person is moving around a circular path, true? So does that mean, that means that in the X axis, the net force required must be equal to mv squared and r, true? Remember, if you move it around a circular path, the net force must be mv squared and r. Here, the center of the circle is along or is towards the X axis. We're going to define that. So F net X must be equal to, we know mv squared and r, because that's the circular plane. It's along the X axis. What about F net Y? Well, think about it. Think about it. Is the object moving up or down? Does this cyclist, as you're traveling around a circular path like this, do I move up or down? No, right? I'm not moving up or down. I'm not changing my height. So the net force in the y-axis must be 0. Okay? So we know what the net forces are going to be now. Okay? What's step 3? Step 3 is to resolve the net forces. What does resolve mean again? To write the expression for your net forces. Okay? So let's look at my diagram. F net X is the total forces along the x-axis. Does FG have any contribution to the x-axis? No, because it's vertical. There is no component in the x-axis. The normal force, however, as you can see, is on an angle. So that means that when you project it into the x-axis, the x component is Fnx. All right? So that's going to be Fnx. Okay? Now, little trick. You always define the center of the circle as positive. So here, if this is my diagram, the center of the circle is this way, to the left, yeah? So that's positive Fnx. We can write that down. Now also, just to wrap things up, instead of writing it as Fnx, we can actually plug in the angles as well. So if this angle here is theta, this is 90 minus theta, this is 90 degrees, so this angle here is also theta degrees, yeah? Okay, Fnx is equal to, take Fn, here's the angle, yeah? You're moving away from the angle, what's the rule? Away from the angle is sine theta. So Fnx is Fn sine theta. Are we done? Is that the only force in the x-axis? Let's have a look again. Yeah, it is, yeah? Okay, cool. Moving on, let's have a look at the F net Y. In the y-axis, how many forces do you have? Well, as you can see here, the gravitational force acts down. But you also have the y component of your normal force. So this component here, we're going to call f and y. And what's f and y equal to? Here's Fn, here's the angle. You're moving towards the angle, it's Fn sine theta. So here, again, taking upwards to be positive, that's going to be Fn sine theta. Wait a minute. I made a mistake, guys. It's cos theta. Sorry, towards the angle is cos. Yep. Fn cos theta times, minus, gravity is going down, so minus mg. Cool? And that's it. This is step 3 done, yeah? So you have the expression for the x-axis, you have the expression for the y-axis. Step 4 is to solve for the unknown, okay? What are we solving for? We are solving for the ideal velocity, v. So what I want to do is I want to make v here the subject. Okay, how do I do that? Well, straight away, as you can see, I can't solve for v yet because I have this unknown normal force. I don't know what that is. So if I want to solve for the ideal velocity, the first thing I need to do is actually remove or substitute out this normal force, okay? And the way you do that is you look at the second equation here. Okay, so that's equation 1, equation 2. We are going to make Fn the subject and then sub it into this equation. Okay, so from our equation number 2, we can see that the normal force is equal to, now I'm just going to do this really quickly for you guys. Take the mg, chuck it over, it's positive mg divided by cos theta. Okay, so mg on cos theta. And when I take that and plug it into equation number 1, I can remove Fn from our first equation. And you're going to get here, this is equal to, I'm just going to move everything up a little bit. Okay, when I plug it in, I'll get here mv squared on r is equal to Fn. We said Fn is mg on cos theta, right? So mg over cos theta times sine theta, okay? So times sine theta. And as you can see, guys, that's going to give you mv squared on r is equal to, now mg sine theta on cos theta is just mg tan theta, right? Okay, and there you go, that's my equation. So from here, all I have to do is just rearrange the formula to give me my ideal velocity. So the m's cancel out, take the r, chuck it over, that's going to be rg tan theta. So v is just square root rg tan theta, okay? And guys, that is how we solve for the ideal velocity. So remember, as long as you use these 4 rules, it's very easy to solve for whatever, component or whatever variable you're looking for, okay? So that's it for bank tracks. I hope you guys understood what was going on, okay? And if you want some more practice, you can have a go at this 2020 past paper here, which was from the Barker Street trial paper. Anyways, that's it for me today. I'll see you guys in the next video.